Hey there folks, welcome to the next episode of Science Show. I'm your host Rifat Bari, and today I'm delighted to have Professor Andrés Cisneros on the show. Professor Cisneros is a physical chemist at the University of Texas at Dallas, where he conducts research on DNA repair and enzyme catalysis. I'll have the chance to ask him everything from the 3 laws of thermodynamics to how he got interested in physical chemistry in the first place. So, if you love science, if you want to learn something new, let's go ahead and hop into the conversation. So, today I have Professor Cisneros. He's a physical chemist at the University of Texas at Dallas. And we're going to be learning about chemistry and physics and a lot of cool stuff in this episode. So, let's get started. Thank you for joining us today, Professor.
Thanks to you for your invitation. It's an honor to be here.
Thank you. So as an undergraduate, I guess my first question is kind of biased. Take me back to your undergraduate years at the Universidad Nacional Autónomas de Mexico. How did you get into chemistry? What made you fall in love with chemistry? Yeah, if you could take us there.
So if it's okay, I'll take you a little bit further back. So I'm originally from Mexico City, in Mexico, and my dad is also a physicist, and he has collaborated over the years with several different physical chemists, chemical physicists, etc. And so in Mexico, they funnel you into the track that you're going to go into in high school. And so one of my dad's friends and collaborators told me, if you're going to go into quantum chemistry or quantum physics, go to physics, don't go to chemistry. And I had a really great chemistry teacher in junior high and then in high school. And so I was, no, I'm going to be a real chemist. I'm going to work in a lab and I'm going to do real experiments. And so fast forward a couple of years, I'm in undergrad and I start doing undergrad research. I went into an organometallic lab, and the fumes and the 24-hour refluxes and stuff like that just wasn't for me. And so I went to my first love, which is computational chemistry and then computational biophysics. And that's what I pursued for my PhD.
Wow. Oh, wow. That's amazing. So you started with experimental chemistry and then you got into computational chemistry.
I did, yeah.
That's interesting.
I realized that the experimental chemistry was not for me. And so I haven't set a foot in a real lab in over 20 years now.
Wow. Well, when I go to like the physics lab, because I'm a physics undergrad, every time I touch the lab material, something breaks. I don't know why. Maybe the lab materials don't like me, but I like computational physics, kind of like for the same reason you got into computational chemistry.
Yeah.
So I mean, it's one thing to get into chemistry, but it's another thing to choose a specific focus. Like there's many different research directions. How did you choose what direction you wanted to go to? So
when I started working in computational chemistry, my advisor, Miguel Castro, worked on density functional theory, applications of density functional theory to metal clusters and computations like that. And we were working on the first supercomputer that was installed in Latin America. It was a Cray YMP way back when. I'm not going to tell you how old I am. But so that was really exciting. And I was fortunate that I was also asked to work as a supercomputing fellow once I started working on all these things. So I really got to know the nuts and bolts of high performance computing from very early in undergrad. And so that kind of led me to search for computational chemistry PhDs, PhD programs. And when I was finishing up my undergrad, there was a joint American Chemical Society, Canadian Chemical Society, and Mexican Chemical Society meeting in Mexico, in Cancun. It was huge. It was ginormous. And when I was there, I got to meet Robert Parr, who is one of the founders of DFT. And I asked him if he was taking students, and he said, no, not anymore, but you could go to one of my students who is at Duke University. And that's how I ended up there, because I got interested in DFT. And then during my PhD, one of the fields that Professor Yang at Duke was getting into is mixing quantum mechanics and molecular mechanics to investigate chemical reactions and biophysical properties of big systems. And by big systems, we're talking about hundreds of thousands to sometimes millions of atoms. And so that has led me into researching biochemistry and a lot of interesting fields. And so that's where I got my start.
Wow, that's interesting. I heard of DFT before, density functional theory, and I know it's kind of used to map out the physics and the chemistry of molecular systems using the laws of quantum mechanics. But I'd like to, maybe in our future conversations we can talk about how DFT works.
Of course.
Yeah. So you did your PhD at Duke University, and so can you tell us a little bit about how you did your PhD? What was your research thesis? Yeah.
Sure. So I had several different projects. I really like collaborating with different people, and since undergrad I started doing that. And I have an interest in simulations of metals because of the large number of electrons. So in quantum mechanics, there are very few problems that we can solve analytically. And so in quantum chemistry, the whole trick and biophysics, the trick is how can we make, let's say, accurate enough approximations to solve many body problems that allows us to really represent the system accurately, right? Mm-hmm. And so specifically when you're talking about metals where you have electrons that are in orbitals that may be quasi-degenerate or degenerate. And so you may have a lot of correlation and a lot of these really interesting electronic features that makes it challenging for computational simulations. And so that's one thing that I've always been interested in ever since undergrad. And so in my PhD, I started working on simulating an enzyme. So enzymes are proteins that catalyze reactions in the body. So catalyst is basically a molecular entity that makes a reaction go faster without consuming without itself being consumed during a reaction. Okay, so there are multiple different catalysts. You can have homogeneous catalyst or heterogeneous catalyst or enzymatic catalysts. And it's basically just some sort of molecule or molecular entity that will facilitate a chemical reaction, okay? Mm-hmm. And so in our bodies and in all of living things, enzymes catalyze the reactions that allow us to live, okay? Mm-hmm. Yeah. And so the question is, if we want to use quantum mechanics to investigate these reactions, which is what we really need to investigate how chemical bonds are being formed and broken, how can we do this for many, many, many atoms and obviously many more electrons, right? Mm-hmm. So one of the challenges with quantum mechanics is that the larger the number of particles you have in a system, the more expensive your calculation, right? Mm-hmm. And depending on what method you're going to use, the order can grow as O(n) cubed or O(n) fourth, O(n) to the seventh in some cases. And imagine if you have 100 atoms and a couple thousand electrons, it gets interesting, right? And some of these biological systems, you can be talking, like I said before, hundreds of thousands to millions of atoms. And so now the question becomes, can we simulate reactions in these systems at an accurate enough level, but making approximations? And so in the 70s, there were, the Nobel Prize was awarded in, I think it was 95, if I remember correctly. 2013, to three scientists, Michael Levitt, Aryeh Warshel, and I forget the third one, I apologize. Mm-hmm. And for this method called quantum mechanics, molecular mechanics, QMMM for short. And the idea is, in these enzymes, the reaction that happens is catalyzed in what's called the active site. And so the active site is a particular region in an enzyme that is, let's say, relatively confined. And then the rest of the protein serves as a scaffold, and there's a bunch of other features that help in the reaction. But for the actual chemical reaction, you can get away with just simulating quantum mechanically the active site and whatever is in the active site. And then the rest, you can use a lower level of theory using classical mechanics and the parametric function that we call force fields. And so marrying those two is what makes it interesting.
So that's the breakthrough, right? So you don't have to separately model each one of these hundreds of thousands of atoms in a biological system. You can just model the active site of the enzyme. Is that right?
That if you're going to use, that would be what we call a cluster model. So in QMMM, you simulate the entire thing, but at two or more different levels of theory. So you use a very accurate quantum mechanical level just for a small number of atoms or particles, and then the rest, you can just do a very low level force field approximation. Okay. And so when I was in my PhD, I started first working on applying this QMMM method to a particular enzyme. It's called 4-oxalocartonate tautomerase. I'm not gonna, I can explain what that means if you're interested, but yeah, the details right now maybe a little bit too far away from the point. But so we use this method to investigate the enzyme, make some predictions. We collaborated with some experimental colleagues in the same department who corroborated our predictions. So that was very satisfying that they confirmed some of the predictions that we made. And so that was one of my first experiences making computational predictions and being borne out experimentally. So that was very exciting for me. And then the other thing that was very satisfying and very exciting about working in the lab of Professor Yang is he's always been interested in not only applying tools, but developing them. And so that was one of the things that I did during my PhD. I developed methods for better calculations, in particular with QMMM. So one of the things that we have to do is when we're doing QMMM, we have to simulate how the atoms are moving with respect to each other. Okay, and so if you have the electrons and you have the nuclei and everything is obviously moving in a time-dependent fashion, you can do what's called either molecular dynamics or Monte Carlo simulation to try to sample phase space. Okay, these are extremely expensive calculations if you're doing QMMM, but one of the approximations that you can make is you can try to find the minima on the on this phase space on the potential energy surface, right? And so finding these minima, doing algorithms for these optimizations is a challenge. And when you're trying to do a reaction, you're not just trying to find one minima, you're trying to find two minima. So what we call the reactant and the product, for example, and the path that connects these two. Okay, and this we call the minimum energy path. But obviously, this is not a 2 or 3 dimensional surface. This is a 3n-6 dimensional surface. So if you're talking about each atom, if you're thinking about it in Cartesian coordinates, each atom is going to have 3 degrees of freedom, right? X, Y, and Z.
X, Y,
Exactly. And so if you have 100,000 atoms, each of them can move in 3 dimensions, right? And then the thing is, we'd call it 3n-6 because the overall rotation and overall translation of the entire system can be neglected, okay? So just from the get-go, you can neglect 6 coordinates, woohoo, right? I mean, if you have 100,000 atoms, that's 300,000 dimensions, right? So it's going to be 299,994, right?
It's not a big deal,
Exactly. But when you're talking about that high dimensionality space, the question is, how do you come up with tools and algorithms to make optimizations that are useful to make these types of predictions? And so that was also part of my dissertation.
I see. Okay. So we talked about your undergrad years at UNAM, how you went to some seminar at Cancun and got exposed to the worlds of QMMM, quantum mechanics, molecular
mechanics.
Something like that. And how you went to Duke for your graduate studies. So that takes us to your current research. If there's nothing I missed in the middle. You want to
Kinda. So from there, I actually did a postdoctoral fellowship.
Okay.
So from there, I went to one of the institutes from NIH. It's called the National Institute of Environmental Health Sciences, or NIEHS for short. And there I was working on developing a force field for classical simulations. Okay. So a force field is basically a set of parametric functions and associated parameters that allows you to simulate whatever system you parameterized it for. Okay, so for example, for water, there are literally hundreds of force fields for water. Okay, and when you're trying to sample phase space, you said that you wanted to talk a little bit about thermodynamics, right? So when you have a system, let's say at a given temperature, let's say room temperature, right? 298, let's make it easy, 300 Kelvin, okay? And you have a mole of whatever your molecules are, you have a Boltzmann distribution of velocities that your molecules are sampling, right? And so this means that you have kinetic energy and you have potential energy, and the potential energy comes from the intermolecular and intramolecular interactions of all your particles in your system, right? Yeah. And so if you can solve the wave function and the wave packet for your entire system, then you will know at an instantaneous point in time all of the information for that particular instantaneous point in time. But then to actually figure out what's going to happen in times forward and backwards in time, you have to use statistical thermodynamics or statistical mechanics. Okay, so you can use different types of ensembles to figure out what is the phase space, so all of the positions and momenta that every one of your particles can sample during a certain amount of time, okay? And at an infinite time, that's going to give you the bulk properties of your system, okay?
Yeah. So the Schrodinger wave equation gives you a snapshot of how your system looks like at one particular point in time, and then you can extrapolate that with statistical mechanics.
Well, so the thing is, you can do the time-dependent Schrodinger equation, and then you can also extrapolate from that. But then to actually get the sampling, then you can use statistical mechanics to do all that. Okay. And so obviously, when you have a large number of particles, it's extremely tough to do sampling with ab initio methods, so quantum mechanics, okay? And so these parametric functions called force fields become really useful, okay? And so these parametric functions are ad hoc, okay? And so there's no, let's say, unique way to build a force field, okay? So
just quick question, when you say force field, can you give like you talked about like how water has many types of force fields, but can you give like a tangible example, like what is a...
Yeah, so for example, we know that when you have let's think about it a little bit easier. If you have two argon atoms or two noble gas atoms, okay, we know that they're neutral, right? So there's no Coulomb interaction between them, but they can form Bose-Einstein condensates, right? Okay. Because of London forces. If you cool them down to liquid helium temperature, basically, you can condense them, okay? And they have extremely cool properties, right? Okay. The reason why they have this is because of London forces, okay? So instantaneous dipoles, dispersion, interaction, et cetera, Pauli exchange. So all of these really cool quantum and classical interactions because of the nature of the particles that make up our atoms, okay? Now, hundreds of years ago, in the 1800s, London and the van der Waals realized we can use very, very simple mathematical functions to reproduce properties of some of these atomic systems. Okay, so for example, the van der Waals function is a function that is basically two terms. One is some constant over r to the minus 6, and another constant r to the minus 12. And if you add them and then measure the distance, this just tells you how much attraction or repulsion two atoms at a certain distance are gonna experience.
Okay. Oh, that's the Lennard-Jones potential, yeah.
That's exactly right. And so if you have a collection, let's say of 100 particles, the only thing that you have to do is a double loop, and then you just calculate the distances and stick them into this function, right?
Okay.
So you can use this as a force field. So the force field is going to be the van der Waals potential that is defined by the van der Waals function plus the force field parameters. So, for example, how big your spheres are, okay? And how strongly or they attract or repel.
Gotcha.
Okay. And so physicists and chemists have been working on these force fields for decades to simulate different types of molecular systems. Okay, so there are several different force fields, for example, for biomolecular systems, so for proteins and enzymes and DNA, etc. There are hundreds of force fields for water. Water is extremely challenging for organic molecules, for solid systems, etc., etc. Okay, and depending on what types of approximations you make, you can query different types of properties for your system. Okay, so one of the things that I was interested in doing was, can we come up with a force field that is as accurate as we can get it to quantum mechanical quality, but still fast enough that we can still do sampling. Okay, so that we can evaluate the terms fast enough that we can literally do, for example, molecular dynamics.
You want the best of both worlds.
There you go. Yes, exactly.
And the quantity. Yeah. Okay.
So that was I was young and naive, or young and ambitious, and so that was one of the things that I went to work with at this NIH institute, right? So when I started working in the laboratory of structural biology, and the reason was my advisor, who is now working in private industry. He was basically an applied mathematician that taught himself quantum mechanics and molecular mechanics, and it's a very interesting story. And he's a super nice guy, Tom Darden. And so he, with his knowledge of math and stuff, he made important contributions for these force fields and for these programs that use force fields for biomolecular systems. And one of his contributions actually got recognized by NIH because he helped during the HIV pandemic for some simulations with an HIV protein that allowed the development of one of the first useful therapeutics. So yeah, he's done some really, really cool stuff. But anyway, so when I started, he challenged me. He was like, so you're working with this QMMM, but we know that the force fields are okay, but we can make them better. So how about we do a force field that is, so one of the approximations that are used in force fields. So when you have noble gases, we already said they're neutral, so you don't have to worry about charge-charge interaction, right? Coulomb interaction. But when you have, for example, proteins are made up of amino acids, and there are 20 different amino acids, okay? And so some of these amino acids are charged, right? And so how do we take into account those that charge distribution? That is one first question. And then the second is, because they're charged, then you're going to have interactions that arise just from classical Coulomb, right? Classical electrostatics.
Yeah.
And so because we can't, if we're thinking about a molecule that has a charge, what you have is the nuclei and then the electron cloud that make up the entire charge distribution, right?
Yeah.
One way to represent that is with functions, and then you have continuous functions, and what you have to do is integrate over all space so that you can capture all of the charge density. Okay? But this is extremely expensive. If you're going to be doing integrals for hundreds of thousands of atoms, it's going to be very tough. Okay? So what a lot of force fields do is they approximate the charge distribution as just point charges. Okay, so instead of having a cloud of electrons around the nucleus, each atom is represented as just a point charge, which is basically the sum of the nuclear sum and then the electronic contribution from the wave function to that atom. Okay, and so there are many ways to do this. This is a field called population analysis, and there are many different molecular charges that can be calculated, okay, depending on what you want to do. So what we decided was, well, we want to bring back the electrons, even if they're not exactly all like the full wave function. We're going to approximate the electron density. So going back to density functional theory, what we decided to do was we're going to have a frozen electronic density that is going to address our nuclei. And so we're going to have to do these electronic integrals, but they're going to be easier because the electrons are not going to be
changing over time.
Exactly. Okay.
I see.
And so we developed this force field, and now one of the things that we've been developing since I was able to take this project on as one of my projects for my career is how do we couple these more advanced force fields for QMMM simulations, and does it matter? And so the answer in both cases is yes. And so we've been playing with that, and it's been very interesting.
So in a nutshell, let me try to summarize to see if I understand. So you have to figure out the force fields for some kind of a system. For proteins, they do have Coulombic interactions because proteins are made out of charged entities, right? So that means somehow you have to take into account those Coulombic interactions. So either you can integrate over the nuclear charge plus the electronic charge coming from the cloud of electrons, or like your big idea was to assume that there's a kind of time invariant electric cloud. Is that right? So
it's not that it's time invariant. It's just that we call it frozen density because of the way that let's call it a fitted density. So we take a collection of functions and we just fit it to reproduce the shape of that electronic density. Okay. And so it's an approximate density. Does that make sense?
Kind of.
So now we have so we have a continuous distribution because the function is a continuous function. So for example, it's a Gaussian. We use Gaussian functions. Sorry.
Yeah.
I apologize. We have, for example, a Gaussian function is an exponential that has r squared exponent, okay, and then multiplied by a constant. And so if you integrate it, if it's just an exponent like that, that's a spherical function, right? And so if you have a spherical atom, a Gaussian gives you a pretty decent approximation of what a spherical atom looks like, okay? But if you have a probe charge and you start bringing in, then you can actually follow, for example, Gauss's law, that if the probe charge is actually inside your charge distribution, then if you have a nucleus inside, like a point charge, then it gets descreened. So it actually feels the electrostatic potential differently if you're outside of the charge distribution or inside the charge distribution. Okay, that's called the penetration effect. Does that make sense?
I mean, I'm just processing this. It doesn't make sense. I mean, can you explain that thing again? Like,
yeah. So imagine that you have an atom.
Yeah.
Okay. So you have the nucleus and you have the electronic cloud. Okay. If you have a probe charge outside of the charge density, then you can represent the atom as just a point charge. That's Gauss's law.
Okay. Yep.
Okay. Now, if you start bringing that point charge, and that probe charge actually goes into the
atom
cloud of the electrons, then because it's inside, there's some probability of the electrons that are going to be outside of that probe charge distance, right? And so now your probe charge is closer to your nucleus, and so you don't get what's called the screening effect, the full screening effect of the electrons for that electrostatic interaction between the probe charge and your atom, because now you're inside that charge density. Does that make sense?
Yeah.
So now you can't approximate the interaction between the probe charge and your charge density by just a single point charge. You have to use the entire integral.
Oh, I see.
Okay. And that's what's called the penetration error, because you would be missing part of that interaction.
So there's as soon as that probe charge enters that electron cloud, there's no way you can approximate it using like that freeze.
Exactly. And now imagine that you have two atoms, right? If the two atoms are infinitely apart, or far enough apart that the charge densities are not overlapping, then you can just use point charges, and that's why force fields work okay.
I see.
As soon as you bring them close enough that they overlap, and for example, they start making a
okay.
chemical bond,
Okay.
then things get really tricky.
I see.
Okay. But you don't even have to make a chemical bond. For example, you know what a hydrogen bond is?
Yeah.
So imagine two water molecules, right? There's actually overlap between the electron clouds of the two waters. There's an attractive density there. So depending on which way the hydrogen bond is happening, okay? And so there's an accumulation of electron density in between two of those atoms that stabilizes that particular orientation and makes that hydrogen bond attractive, okay? And so you can approximate it with a combination of the van der Waals function and the Coulomb charges. And so for some orientations, you can get it okay. But the thing is, these Coulomb charges and the van der Waals are all spherically symmetric, okay? But then if your molecules start moving around, the energies that are going to be calculated with the van der Waals and the Coulomb charge are not going to be accurate because you are missing that penetration charge. Okay, so the force field breaks down.
Oh, okay. So
and that's why you need a better force field.
I see. So okay, so we have these two big ideas. We have the idea of the force fields, and that helps you predict how these systems interact with each other, right? So you have, for example, Leonard-Jones r to the -6 and r to the -12. That's your force field. But then you have to think of the additional complication of what if the electron clouds get too close to each other. That's when you have to think about the penetration problem.
That's exactly right.
I see. And that's when you're forced to actually integrate over the electron cloud.
That's exactly right.
That sounds really cool.
Thank you.
Yeah. So now can we talk a little bit about like thermodynamics and
Sure.
So you talk a little bit about like the famous 3 laws of thermodynamics. What's your take on them as a professional chemist and physicist?
So to us they're fundamental. Okay. So obviously for all physicists they're fundamental, but for example, for developing force fields, one of the force fields that we've been developing based on these molecular densities is a force field for water. Okay. And so obviously, energy is not created or destroyed, it just gets transformed, and then maximum entropy. So for Zero's law, first law, and second law, right? And so basically, as you start building your systems, let's think about the box of water, okay? And we're trying to simulate how the water is going to behave at different temperatures, okay? So when we're in the lab, we can measure all sorts of different physical properties, right? So we can measure thermodynamic properties, we can measure transport properties, we can measure dynamic properties, etc. Okay? If our model is accurate, we should be able to match the experimental prediction to certain accuracy, okay? And depending what the purpose of it is, you may want your force field to, for example, simulate only liquid or condensed phase, okay? Or ice, or gas phase, or liquid gas interfaces, okay? Depending on what your aim is. Ideally, your force field should be able to do absolutely everything, right? And not only bulk properties, but also spectroscopic properties, okay? This is the reason why there are literally hundreds of water potentials, because water molecules experience are not only quantum in terms of electrons, but also in terms of nuclei. So you have to take into account electronic quantum effects and nuclear quantum effects if you're actually going to model this properly. Okay, so this has been something that has been fascinating for me since I was a young professor, and I was fortunate to be invited to a conference that was exclusively on water. It was called Water, the Most Anomalous Liquid. It was sponsored by the Nobel Institute, and it was in Stockholm. It was very fun. Anyway, and so there were a bunch of modelers. It was a whole month thing. We were just there for a week. And there were a lot of experimentalists. And so we had a chance to just literally eat, sleep, and drink water, I guess, and water simulations. And it was super fun. I got to learn tons. But one of the things that I learned was even though there are all of these force fields, there are a handful that can actually really get to the accuracy that is needed for some of these property predictions. And so this is where all of these laws come from. So for example, if you're thinking, if you have your system at 0 Kelvin, okay, then the system should be perfectly predicted by just the potential energy terms in your force field, if your force field is accurate, okay? Or if you have a perfect a way to calculate the wave function, or ab initio, okay? But then you start raising the temperature, because that's when fun starts, right? And so even in ice, or if you have super liquid, super cooled water, then there's this whole interesting field in the water community about the Witham line, that if you have super cooled water, depending on how you get to it, you're going to have high density water or low density water, okay? And so and this all has to do with entropy and how you're traversing through the phase space of the water potential, okay? And so this is the intersection between potential energy and kinetic energy, and kinetic energy is going to determine all of the entropic effects, and the potential is going to determine all of the enthalpic effects. Not all, but most, okay? And there's a bunch of other cool things that come in through thermodynamics. But let's get away from that and just go to condensed phase. Now let's say that we're at room temperature and we're simulating water, then depending on the temperature that you're at, if your potential is not accurate, then the interactions between your water molecules at the atomic level are not going to be accurate. And so this is what's going to determine through statistical mechanics what the bulk properties of your system are, right? So for example, the temperature. If your system is too, let's say, attractive, then the molecules may not diffuse in as fast as they should, because they're basically too sticky, right? And they're driving together, for example, clusters of water.
So like that would lead to a high viscosity or something like that.
Exactly, high viscosity and higher density at the same temperature, which is not what you want, right? Because you're not reproducing the correct properties, okay? Or if it's too soft, then it's going to be too light, right? Exactly, less viscous, et cetera, et cetera. So everything comes into play, from statistical thermodynamics, quantum mechanics, everything. So yeah, that's some of the things that we think about. And the same thing applies for enzyme reactions. Okay, so we have to think about the thermodynamics of enzyme reactions. So I mentioned this reaction profiles, right? So you have the 2 points, reactant and product, and then you have the path that connects them. If you think about it at 0 Kelvin, it's just a line, okay? But we know that systems don't live at 0 Kelvin.
Wait, a line? Right? What do you mean by a line?
So you can think of it it would be like a hyperline. So basically, we call it the reaction coordinate. So imagine that you have a system that has 100,000 atoms. Yeah. Okay. But your reaction only involves a transfer along one single dimension. Okay. Okay. So you're transferring one single atom, let's say a proton, along one single dimension. Okay. In that case, you can calculate your reaction potential based on that single dimension. Okay. Okay. I see. Yeah, it's like a dimensionality reduction. Okay. Okay. And so at 0 Kelvin, it would be just calculating the potential energy at every different distances that proton travels. I see. Okay. Okay. Now, if you start increasing the temperature of your system, then the proton is going to start moving around. Yeah. Sure, right? Sure. And this is especially protons, they like to go wherever they want. And so this makes things interesting, because it's not going to be only enthalpic effects, but also entropic effects. So the second law becomes super important. Okay. And so you're going to have an enthalpic component. So now we're going to be talking about reaction free energies. So you're going to have TDS plus DH. Okay, the change in enthalpy plus the change in the temperature-dependent and entropic term.
Yeah.
Right.
Okay.
And so all of this is a huge part of physical chemistry.
I see.
Okay.
When you said that kinetic energy takes care of entropy and potential energy takes care of enthalpy, could you kind of expand on that? What is your view of entropy? Because the popular definition of entropy is disorder, but sometimes that's not always true. As I understand it, entropy is the total number of ways you can arrange your system, or the constituent parts of your system. So if you that's how I think of it. But how would you explain it to a lay audience?
Yeah, so I tend to think of it depending on the, let's say, on the problem at hand. Mm-hmm. So sometimes it's useful to think of this toy approximation of like increase or decrease of disorder, right? But it's not only enthalpy. So the thing is, thinking about entropy by itself and enthalpy by itself can lead sometimes to some confusion, because they're linked together through the internal energy, right? So it's U is equal to dH minus TdS, right? Uh-huh. So it's the entropy balance that matters, not just one or the other. Okay, so you're right. Like thinking about it as all of the possible ways that you can that your system can adopt. This is the phase space sampling. Okay, so all of the positions and all of the momenta. Yeah. Right. Mm-hmm. That your system can take. So all of the positions, that's going to give you the potential energy. So how you can arrange all of your atoms, and you're going to have your interaction energies, intra and intermolecular and interatomic energies. That's going to give you the potential energy. And then the momenta, that's the kinetic energy, right? Mm-hmm. And that's going to come. So there's a direct relationship between kinetic energy and temperature. Okay? As you start raising the temperature, your kinetic energy is going to increase. Uh-huh. Right? And so those two are linked together.
I see. So it's like two sides of the same coin.
That's exactly right.
Can you think of it as you do potential and kinetic energy? Their sum is conserved in the form of mechanical energy.
That's exactly right.
Can you think of entropy and enthalpy, and do they have a similar kind of relationship, or?
So the thing is, it's not exactly just like kinetic energy and potential energy that go directly to enthalpy and entropy. Okay. It's a little bit more than that. But there's the virial theorem is the one that relates kinetic and potential energy, and basically just says that your total energy is conserved, and the kinetic energy and the potential energy are anti-correlated, so that when you add them up, your total energy is always conserved. Okay, so if your potential energy decreases, your kinetic energy has to increase to maintain your same energy. And this is one way, for example, when we're doing molecular dynamic simulations, and we're using an ensemble that's called canonical. I think that, I don't remember my ensembles, but if we're using the canonical ensemble, which is constant number of particles, volume, and energy, then if our integrator and our integrals are correct as we propagate the system, all of these simulations are done by integrating the Newton's equations numerically, the classical Newton's equations numerically. Yeah. So if you're not losing energy, you should see that your kinetic energy and potential energy are perfectly anti-correlated, so that you can maintain your total energy.
I see. So we talked about entropy, enthalpy, the laws of thermodynamics. We talked about your career. I wanted to talk a bit about the free energies, the Gibbs free energy, and God, it escapes me right now at the worst possible time.
Helmholtz?
Yes, Helmholtz free energy. Yes. So can you shed some light on what those are, how they work for a lay audience?
So this is the bread and butter, and sometimes the bane of our existence. So we're interested in, because we are physical chemists or chemical physicists, part of our interest is in simulating these enzyme reactions, right? To simulate these enzyme reactions, what we have to calculate are the free energies of reactions and free energies of the barriers that connect these different points along our potential energies, okay? Our free energy surfaces. And so the free energy, depending on how you're doing it using Maxwell's relations, the Gibbs free energy is the free energy calculated at constant number of particles, pressure, and temperature, NPT, okay? And Helmholtz free energy is the equivalent, but with the volume constant instead of the pressure, okay? And so experimentally in the lab, it's much easier to calculate Gibbs free energies because it's much easier to have a constant pressure experiment, right? Instead of a constant volume experiment. Computationally, it's a lot easier to do NBT simulations. And so there's this whole thing about Gibbs and Helmholtz, and it does make a difference, right? But in our case, what we're interested in is the free energy difference, be it Helmholtz or be it Gibbs, between the different points along our reaction path, okay? And so in physics and in chemistry, when we're looking at processes that involve some bond breaking or bond forming for a molecule, or even going around bonds and stuff like that, we have this concept called the transition state, okay? It's the transition state theory. There's a whole very interesting mathematical foundations from Kramers and Eyring, going back decades. And so this concept is linked to the structure and the thermodynamics of the arrangement of your atoms in your molecule as a reaction is happening, okay? And basically, if you think about it, the same example that I was telling you, that you have, let's say, a proton that is traveling in between two atoms, okay? If the two atoms are exactly the same, let's say that you have a water and a proton is going to be transferring in between.
It's symmetrical.
Okay.
Yeah.
Exactly. If your system is symmetrical, then when you plot the positions of all of your atoms in your system with respect to the energy, this devolves in what we call the potential energy surface, or the free energy surface, or if we're calculating free energies at a given temperature, so considering enthalpies and entropies. Okay. And so if your system is symmetrical, the two bottoms, so the two minima, the reactant and the product, should be equivalent in energy. Okay. Isoenergetic. And as you start moving your proton towards the middle, you should reach a maximum. Okay. The structure that corresponds to that maximum in energy, that's called the transition state. Okay. And so the definition, depending on which theory you're looking, so Kramers or Eyring, it's a fleeting intermediate that cannot be captured, and it defines the separation of it's the hypersurface separating the reactants from the product.
Okay, so that's the significance of the transition state.
That's exactly right.
The product, the reactant, and this is the middle cutting
That's
point.
exactly right. And so you can actually relate the energy difference between the transition state and your reactants or products to the reaction coefficients that you can measure experimentally. Okay, so the reaction coefficient tells you how fast the reaction happens in the bulk. Okay, and so some reactions are extremely fast, some reactions are extremely slow. And the way you do this is you literally start measuring at a bunch of different time points the concentration of some particular element of your constituent of your mixture, so some reactant or some product. Okay, and there's it's really beautiful. This is called reaction kinetics and reaction dynamics, and you can actually measure these reaction coefficients and reaction rates. And so this reaction rate is related to the difference in energy between the reactant and the transition state. So the higher the barrier, the slower the reaction is going to be. It's inversely proportional. It's actually exponential. It's an exponential decay because
the higher the barrier. What barrier? What are you?
So the barrier is defined as the difference in between the minimum. So your reactant, so the energy of your reactant and the energy of your transition state. Okay. So if you have to give it a lot of energy, then your reaction is going to be slower. Okay.
Makes sense.
If your barrier is very short, then or very small, then the reaction is going to happen really fast.
I see.
Okay. And this has to do with the temperature. right? Because there's an enthalpic and then an entropic component.
I see.
Because it's all related to the free energy, okay? And so that's why in chemistry, a lot of reactions happen at high temperature, because when you give your molecules kinetic energy, then they can start colliding with each other. And some of those collisions are going to be productive and are going to lead to products.
And some of those collisions are going to get over the barrier required.
They're going to have enough kinetic energy to collide in the correct orientation to go over that barrier. That's exactly right.
I think Richard Feynman phrased this as there is a hill and there is a ball on the other side of the hill, and the ball over here doesn't know that it wants to connect with the ball on the other side of the hill unless you give it enough energy to roll up the hill and get over.
That's exactly right.
So in closing, so we've talked about your career, how you got into physical chemistry. We talked about some of your current research in DNA and enzyme repair. We talked about thermodynamics, which will help me in my own research. And so now I want to talk a little bit about advice for the people who are watching this. Most people who are watching this will maybe be undergraduates or even high school students who are interested in science, math, engineering, technology. So what advice would you give to them for pursuing their passion or becoming a professor or a scientist?
So my first piece of advice would be listen to or ask many people, because different people are all of the advice is based on personal experiences, right? So my personal experience may be different, or it's likely different than a lot of other people's, right? So for me personally, what really was very useful was having a big network of mentors, both peers and older scientists, that were very encouraging and were very helpful. So for example, one thing that if I can digress for 2 minutes, when I was a postdoc at the NIH, in addition to working on these force fields, I was working in collaboration with experimental groups looking at these DNA repair enzymes. So we were interested in figuring out what these DNA repair enzymes do. And this is how we got into DNA repair and learning about all sorts of different biochemistry and structural biology and all of these things. And so when I was an undergrad, I took a little bit of biochemistry, but nothing prepared me to the level that these top, like literally world-class scientists were working at, right? And so one of the things that I took upon myself was teaching myself a little bit more biology and structural biology. Part of the reason was I was working with these people. The other part was also kind of selfish, because I tried to get some grants. As you know, getting fellowships and all of these things is really useful and for all sorts of different reasons, right? Namely, getting money. And so I was trying to get money. And one of the reviews that I got for one of the fellowships that I applied for was, this person should learn biology first. Because my application had a lot of DNA repair and all of those things. So that kind of stung. I was like, that I'm trying to do all of these really cool QM calculations, right? But they were right. I had to learn biology. And in my case, because of the stuff that I was interested in, it was not just coming in with my hammer, my quantum or QMMM hammer, and trying to apply it to like the DNA repair nail. I had to know what I was going to do with it, right? How I could apply it. And so my advice is, if you have something that you're extremely good at and you're trying to apply it to something that might be a little bit off field, don't be afraid, or be curious enough and humble enough to realize that there's a lot of knowledge and background knowledge that has been generated in that adjacent field that is going to be extremely useful and extremely important. And so getting to know that other part is going to be very, very beneficial.
Wow. Yeah. Thank you for that advice. It kind of reminded me of I'm not going to share the full story now, but there was a problem that I I worked on for a few months called the triangular billiards problem. It's an open math problem. And I refused to look at the literature because I thought I had an idea, a machine learning idea that would crack the problem. Obviously, me being naive, just like you said at the beginning, you wanted the best of both worlds. I thought that I could come in with an AI hammer and strike the blow. Sadly, the blow struck me. So yeah. Anyway, thank you for that great advice. Would you do you have any advice for graduate students who are wondering what research topic that they should do their PhD in, or what focus they should head towards?
I could be selfish and say biophysics is where it's at, but I mean, it's really, I guess my advice would be, don't be afraid to be curious, and obviously within bounds to, I'm not going to call it fail, but to be able to get humbled. So for example, when I was an undergrad, I said I started as an experimental chemist, and then I realized, no, that's not me. So like that, but obviously you don't want to be testing and going after all sorts of different fields that can actually hinder your progress in the program. Okay. And so within the bounds of the particular programs, if you have multiple different interests, if it's possible, try to explore and maybe even see about merging some of these fields that might be, I don't know. So for example, cosmology and physical chemistry, and then you get astrochemistry, right? And so stuff like that.
Just like you merged biology, chemistry, and physics all into one. That's amazing. So thank you, Professor, for your time and for your advice. I think a lot of our audience who are aspiring scientists and aspiring STEM folks will find it useful. So thank you for taking the time to talk with me today and to be on the show.
Thank you very much, Rifat. It was fun. I really enjoyed talking with you.
Likewise.